this. Last week we finished on Friday, or the last week we were in school, we finished on Friday with momentum and collisions. I gave you some notes and there were some practice problems that we did most of together. I don't think that I assigned anything going into the next week. It was just, hey, how much can we get through as we're going through this work? In class today, what we have listed is, I'm going to show a warm up here in a second. Then we're going to go into center of mass, take a little bit of notes, not quite as many as we did last time. And then I'll start both practice sheets with you so that you can get a good starting and orientation, kind of a, where should your head be? How should you be approaching these? I'll get you started. I'll let you finish those up. They're really not bad at all. We should be able to click through this pretty fast. So let's start with a warm up and see what we have. I'll zoom this in a bit. It looks kind of small on the screen, and do it where we can see it all together. All right. This has a 1,500 kilogram car moving at 8 meters per second. And it says it rear ends. That means it hits another car from behind. So the second car is like sitting at rest. Maybe it's at a stop sign or a red light. And then this 1,500 kilogram car moving at 8 meters per second runs into the back of this other car. Rear ends a 500 kilogram car that is initially at rest. Both objects stick together on impact and move with a speed of 6 meters per second. So when they impact, they stay then as one mass. We remember that this is an inelastic collision, meaning that before the collision, the total momentum of the system would be the mass of car one times the velocity of car one, which would be 1,500 times 8, plus the mass of car two times the velocity of car two, 500 times 0. So we'd have 1,500 times 8 plus 500 times 0. When you calculate that, that's total momentum of the system before the collision. We know total momentum of the system after the collision must equal the momentum before, because it's conservation of momentum. After the collision, those cars are combined. You have one big mass, car one plus car two, 1,500 plus 500 times the velocity of that combined mass, 6. Now that we've got an orientation, we have an understanding of what's going on, let's take a look at the questions. It says, describe the impulse that the 1,500 kilogram car experienced from the wreck. And then let's go ahead and look at number 2 at the side. Describe the impulse that the 500 kilogram car experienced from the wreck. I want you to take just a couple of seconds and think about that. And when you have something, I want to hear some words from you guys. It's been a long time since we've been together in class. So let me hear from you and tell me something that you know that would help answer number 1 and number 2.
Impulse is mass times change in velocity over change in time.
Say it one more time so I can hear you clearly.
Impulse is mass times change in velocity over change in time.
Okay, so I'll take impulse is mass times change in velocity. Don't include time there. So I like where you're starting at. So the question says describe impulse, and your first, the first thing that I've heard is a definition of impulse, which is perfect. It's a good place to start. Using a physics fact and saying, okay, I can factually state, well, what is impulse? Impulse can be defined one of 2 ways. It's either force times time, or it's described as mass times the change in velocity, because impulse is a change of momentum. Impulse is a change in momentum and can be calculated as force times time or mass times the change in velocity. Now, in this problem, we have not been given a force. We have not been given any time. So as far as force times time, can't really use that here, can we? Here we need to be able to say, okay, well, do we have mass and a change in velocity? Well, yes, we do. So let's take a look at that and see what we can do with it. Now, if this was an FRQ, I would definitely want you to describe this in words the best you could. And starting with saying that impulse is a change in momentum and can be defined as mass times the change in velocity. That is a perfect way to start it. Now, if we actually want to calculate it, let's look at the calculation, because I think that getting through the calculation helps to understand, but you still need to be able to put it in words. Okay. So let's look at the calculation. Here we're going to have impulse is equal to mass times the change in velocity. Okay. We already understand the words, the concepts behind it. We spoke of that, but let's actually look at the math and see how this comes about. So this is, what they say, 1,500 kilogram car. And the change in velocity is it finishes, the final velocity is 6. The initial velocity was 8, final minus initial. Okay, so 6 minus 8 would be -2. -2 times 1,500 would equal -3,000, right? And the units is Newton seconds, because it's force times time is one way to calculate it. So we're going to use Newton seconds as our impulse unit of impulse. Now that we've done number 1, can someone tell me what should we expect for number 2? What do we anticipate?
It should be the same.
It is the same. You're exactly right. Now I heard you saying it is the same, but behind your voice, I thought I heard someone starting to ask a question. Was someone asking a question?
Yeah, I had a question.
Yes.
You said impulse is only mass times change in velocity. But then I thought impulse was also like mass times acceleration. But isn't acceleration like change in velocity over change in time?
Remember, force is mass times acceleration, okay?
Right.
Momentum is equal mass times velocity,
Okay.
okay? An impulse is equal to a change in momentum. Well, a change in momentum isn't going to come from a change in mass. Masses don't change, but velocities do. So
Okay.
impulse is equal to mass times a change in velocity, and it also happens to be force times time. So impulse is mass times change in velocity or force times time. Now, if I want to divide time over, I could say that mass times change in velocity over time is equal to force, because let's do that. Let's divide both sides by t. And then the t's cancel here, right? And let's just work this down. We would say that mass times a change in velocity over time is equal to force. Well, that's perfect, because change in velocity over time is acceleration, and we know mass times acceleration is force. So we can kind of derive right back to Newton's second law. It's amazing how Newton's second law just keeps coming around, and we use it to derive everything that we're doing, it seems like. But if we just go back to this, that just kind of shows we can work this backwards and say force is equal to mass times acceleration. We can work it backwards all the way to say that force times time is equal to mass times a change in velocity. And that is what impulse is. Impulse is a change in momentum and can be calculated as either mass times change in velocity or force times time. And we can set mass times change in velocity equal to force times time, because they're both impulse, so they're equal to each other.
All right. I understand a bit better now.
Okay, perfect. Now, before we went on that tangent and started talking about that, the statement made about number 2 is they should be the same. Can someone else tell me, why do we believe the impulse is the same for the 1,500 kilogram car as the 500 kilogram car? Do we have any supporting information to say why they would be the same?
Newton's third law?
Yes, Newton's third law. Now, I want to bring, there's a note in the chat, and it says, what is N times S? That is the unit for impulse, which means Newton seconds, like Newton's times seconds. Because remember, we're multiplying, we could multiply force times time, right, to get impulse. The unit of force is Newton, the unit of time is seconds, and we're multiplying them, so the unit becomes Newton seconds, N times S. And when I ask the question, what supporting evidence do we have? Absolutely. Newton's third law says that the force will be equal but opposite between the two interacting objects, right? The two cars. So we know the force is going to be the same. Well, that's the F in the F times T. Well, what about the time? Is the time going to be the same? Certainly so. One car hits the other, they hit each other. One car doesn't experience the accident for 5 minutes while the other one experiences it for 2 seconds. That would be weird. The impact is the same between the two automobiles. Newton says the force is the same. Well, if the force is the same, but in opposite directions, and the time is the same, that means the magnitude of the impulse should be the same, but in the opposite direction, right? So let's take a look at it. Let's prove it just to make sure that, Mr. Watley didn't forget to drink his coffee, which I don't drink coffee, but let's just make sure that the teacher isn't having, the first period jitters and is getting things wrong. So let's answer this, or let's calculate it. We have impulse, again, is mass times the change in velocity, final minus initial. In this case, for the 500 kilogram car, it's 500. The final is still 6 because together they're moving at 6 meters per second. And the initial for the first car, it was at rest. At rest means 0. So we're going to say 6 minus 0, right? That would be 500 times 6 minus 0 is still 6. 6 times 500 is 3,000. And the unit is still Newton seconds. Okay, don't get hung up too much on the unit. It's just like, okay, well, wait a minute. I multiplied mass times velocity. Wouldn't it be kilograms times meters per second? Sure. But it's also acceptable to say you could be multiplying force times time, which is Newton seconds. I'm going to be consistent and just use Newton seconds. I don't want to confuse anybody and say, well, why did you use that unit here and this unit there? I'm just going to be consistent with Newton seconds. Okay. So yes, the impulse is shared. The impulse is the same. And it's based on, just like he said, Newton's third law. All right, so let's take a look and see what number 3 says. How does the magnitude of the force that says care, that should say car, each car experienced in the wreck compare? Well, the magnitude of the force has to be the same. It says justify the answer in a paragraph length response, Newton's third law. Newton's third law says that they're going to share the same force. It's going to be equal magnitude, but in opposite directions. Your paragraph doesn't have to be a long paragraph. A paragraph can be a sentence. A paragraph can be 2 sentences. Ideally, a paragraph's not going to be 6, 7, 8, 9 sentences. But in 1 or 2 sentences, I'm sure you can come up with a way to state Newton's third law and how it applies here. I'm positive of that fact. All right. Okay, so that gets us through our warm-up. We can take a breath. We can say, okay, it's not so bad, right? I told you momentum is not going to be awful. Today, we're going to talk about center of mass. We're going to do a little bit more work with impulse. Next class is going to be on Thursday. Thursday and Monday, we're going to progress our knowledge just a little bit. That's going to get us into next week on Monday. I said Wednesday of next week, I believe we're doing review stations. I don't have the details on them today, but just to kind of looking down the calendar, Friday of next week will be the last test date of this semester, this grading period. So that's Friday of next week. The week leading into winter break, which would be the week after that, 2 weeks from right now, will be when retesting is. So that's kind of where we're working towards. We're going to learn a little bit today. We're going to do some more work on Thursday, a little bit of learning on Monday, review Wednesday, test on Friday. So that's our 2 weeks, this week and next. Let me make sure there's nothing in the chat. And there's a time impulses are different. I'm a bit confused. Is there a time the impulses are different? No, the impulses are going to be the same. When you have a collision, we've got 2 objects and they're colliding. The force is shared, the time is shared, so the impulse is going to be the same in magnitude. The magnitude is the same. The directions, we know the force is going to be in opposite directions, but the magnitude of the impulse will be the same. And it's based on Newton's third law. Okay, let's take a look and see what we're going into today. I've got my notes in front of me, so let's just take a look at this. So in every type of collision or explosion, the total momentum of the system will always be conserved. Okay, we talked about this last class, but it's been a little while, right? We all had some time off. Hopefully you weren't studying and working. Hopefully you took a little bit more time to sleep in. So let's remember, in every type of collision or explosion, the total momentum of the system will always be conserved. We talked about inelastic collisions, elastic collisions. We talked about explosions. Whatever momentum is present before the action must also be the only amount after. How do we calculate that? Well, if we've got 2, in this case, in the warm-up, we had 2 automobiles. momentum of automobile 1 plus momentum of automobile 2. Add that together. So mass times velocity plus mass times velocity, or P1 plus P2, because momentum is P. Add the momentum before, set that equal to the momentum after. As long as you know the momentum on one side of the equation, or either before or after the collision, you know the momentum on the other side, okay? Because it's always going to be equal. Only in elastic collisions. The elastic collisions are when they bounce off, okay? They hit and propel. Think of the little ball, you know, the balls you put on your desk, and they hang by a little fishing line, and you pull it back, you drop it, and it sends it back and forth, that sort of thing. That's an elastic collision. It's bouncing off, right? It hits and it doesn't stick. It's only in elastic collisions will the kinetic energy of a system be conserved. Only in elastic collisions will the kinetic energy of the system be conserved, right? Because in an inelastic collision, you could have two objects coming towards each other, hit and come to a stop. If it comes to a stop, the kinetic energy is not being conserved. Or if it hits, if both are going really fast, well, I guess in that case, it would bounce. Or what if they're coming really fast and then they finish going slowly one way? Like this one's going really fast to the right, this one's going slow, and they hit. So it's only in elastic collisions the kinetic energy of a system is conserved. This means that no object in the system can lose velocity with respect to the center of mass. In an elastic collision, this means that no object in the system can lose velocity with respect to the center of mass. Don't worry, center of mass, new term, we'll define it, okay? In inelastic or perfectly inelastic and explosions, some or all of the kinetic energy is translated to another type. All right, let me step back. I know I'm saying this a couple of times because I want to make sure that you can kind of take it in. I will write on the screen in a minute so that way you can kind of write along with me, but I'm just going to read this through one more time. Only in elastic collisions, only elastic collisions will the kinetic energy of a system be conserved. That means kinetic energy before is equal to kinetic energy after. Momentum is always conserved. Kinetic energy is only conserved with elastic collisions. This means that no object in the system can lose velocity with respect to the center of mass. In inelastic collisions, or perfectly inelastic and explosions, some or all of the kinetic energy is translated to another type. For inelastic, objects lose some velocity with respect to the center of mass. Perfectly inelastic, objects lose all velocity with respect to the center of mass. And explosion, object starts with the same velocity as the center of mass. All right, so I'm going to write down a little bit of this so that way you can kind of catch up and not seem too lost. Let me bring up my little screen. And let's zoom this in a little bit. Okay. So in inelastic, perfect inelastic, and explosions, some or all of the kinetic energy is translated to another type. So for inelastic, we said objects lose some velocity with respect to center of mass. Let's see, objects. All right, just in case my handwriting is awful, which it looks like it is a little bit this morning. Inelastic, objects lose some velocity with respect to center of mass. For perfectly inelastic, here objects lose all velocity. And then I'm going to just put with respect to center mass. WRT is with respect to CM, center of mass. It ends, the sentences end the same way. Perfectly inelastic objects lose all velocity with respect to the center of mass. Inelastic objects lose some velocity with respect to center of mass. Finally, explosion. Objects start with same velocity as center of mass. Objects start with same velocity as center of mass. So then we come into the question is, what is center of mass? What is center of mass? So center of mass this is the average location of mass within an object or a system. So something popped in the chat. Let's take a look. What's the difference between inelastic and perfectly inelastic collisions? What's said on the screen? With inelastic, they lose some velocity. Perfectly inelastic, they lose all velocity. So with inelastic, when they impact, when they collide, they stick together. Do they stick together and stop, or stick together and still have some velocity? So your differences in definitions are going to be based on what you see on the screen. Whether or not they lose all velocity with respect to center of mass, or they lose some of the velocity with respect to center of mass. What is elastic again? Elastic is when they bounce off of each other and they don't combine. Think of a basketball and the floor of the gymnasium. That basketball bounces off of the floor. It's an elastic collision. But if you took an ice cream cone and tried to dribble it like you do a basketball, it's going to hit the floor and stop, right? That would be an inelastic collision. It hits and that mass combines, right? They are stuck together. Simple example, kind of silly, but you get the idea. Elastic bounces off, inelastic combines. The masses combine.
Mr. Watley, I have a question.
Yes.
For the elastic ones, they will always have the same velocity, right?
What do you mean they have the same velocity?
Is it only for inelastic and explosion that we're talking to velocity with respect to center of mass?
Right, because with elastic, the reason I said is, what do you mean by keeps the same velocity? Because when I use the basketball analogy, when the basketball hits the floor and it bounces back up, the velocity has changed because the direction has changed.
Okay.
So that's why I didn't want to say that the velocity stayed the same. The magnitude of the velocity stayed the same, but the velocity itself had to change because it changed directions. But yes, the idea would be it's bouncing off. It's maintaining its kinetic energy, right? We could say the kinetic energy is the same because their direction doesn't matter. Once you
Right.
square velocity, the direction goes away.
Right. And is momentum always maintained for all of these?
Yes, momentum is maintained.
Like
This
even
is conservation of momentum. Momentum is not changing.
like even for elastic, inelastic?
Yes.
All right.
And I gave you those equations last class. If you don't have them, look back to the recordings posted. Look back to that where I said, where we had it before is equal to the after, and we did it for elastic, inelastic, and explosions. Those are good equations, not that you would have to have them written out to apply them, but it's more of an understanding what's going on. And then you would be able to just say, okay, it helps you clearly see that your momentum is equal because we set them equal to each other in those equations and said, this is what it looks like before, this is what it looks like after, and it's set equal. Someone asked what would be an example of perfectly inelastic and just regular inelastic. I hate to use car wrecks because a lot of people have real life experiences that make car wrecks a example, but it's kind of one that fits. When two cars collide, if they collide and they lock together, do they hit and they stop, or do they hit and still have some velocity, some motion? Are going to be just when things collide, it's like, do they hit and stop? Do they hit and still have some velocity with respect to center of mass? That's where your best examples come from that. If we were in class, I've got like a rail with little carts, and I can make them collide and hit and stuff like that. So it's a visualization, but not one that I can do practically through Zoom, at least not today. Maybe before the test, I'll try to set it up to where we can see it like a demo through the Zoom. Let me go through and finish getting the notes down. That way we can get into the practice work. I don't want to bog down too much. The only reason we're talking about center of mass, or the only reason we use center of mass, is we reduce objects or systems to their center of mass just for simplicity. So we can kind of say where the center of this system is and how do things around that center deal with things. Now, if the system is one thing, like one person, the center of me would be, like center of my body or whatever. But if it's me, or if it's like bumper cars at the fair, I know the fair wasn't really a fair this year, but if we're talking about the two bumper cars, we would take the center of one, center of the other, and kind of see where that average center is for that system. It's like, okay, well, how do we do that? How do you actually determine where the position of the center of mass is? Well, I'm glad you asked, because that's the next thing of our notes, right? I know I'm the one that asked, but whatever. You got to just take it for what it is. All right, so position, center of mass. So let me just title this position of CM, and CM, center of mass. Okay, it'll be my shorthand for center of mass, CM. Okay, so let's say that we've got a system, and this is a 2 kilogram object. And then here, go a little ways away, let's put a 1 kilogram object. And then just a little bit ways away, let's put a 4 kilogram object. And we need to determine where's the center of mass. And let's say that this is 3 meters away, and then this one is 2 meters away. Okay. It's like we need a strategy. We need to know, how do we actually try to get to a center of mass? Well, the center of mass, we're going to define as like the position. We know X is position and the position of center of mass. So X CM. Okay, nothing exotic here. We're just saying that the X is a position. We've always used X as position in physics. And here I'm just saying position of the center of mass is going to be able to be defined as M1x1, M1x1 plus M2x2 plus M3 x3. Well, now what is that? The mass of 1 times the position of 1 plus the mass of 2 times the position of 2 plus the mass of 3 times the position of 3. And that can go on and on and on for however many objects are there. And that's going to be divided by the mass of 1 plus the mass of 2 plus the mass of 3, on and on and on. So you're going to take, this is like momentum. We were taking mass times velocity. But here, since it's the center of mass, we're going to take the mass times the position, plus the mass times the position, plus the mass times the position. So it's like momentum, but it's position instead of velocity. Okay, and then we're just going to divide by the total mass. Now, in regards to position though, we need to know like how far apart they are. Well, where do we start? Because you need a starting point to know how far away something is, right? You have to have a starting position. So if it's not specified, if the problem doesn't tell you where to start, you're going to start at the far left side. Just like reading, well, at least in English, we start on the left and we read to the right. So if the problem doesn't state otherwise, start on the left. So that means my starting point is going to be on the far left side of my example. So here I would say that my position of my center of mass is going to be equal to, now if I start on the far left side, what is the mass of the 2 kilogram object? I forgot the G. The mass of the 2 kilogram object is 2 kilograms. what is its position? Exactly right. I see it with the hand signals. So I'm going to write it out so that way no one says, why did you drop it? I'm going to have 2 times 0, because we're starting at the left side, plus my next mass is a 1, and it's 3 meters away from the position. So that'd be 1 times 3. Plus I have a 4 kilogram object, and that 4 kilogram object is 5 meters from the beginning, right? So don't just say, oh, it's 2 more meters over. No. How far is it from the beginning? So don't lose that. It's going to be 4 times 5. And that's going to be all over the total mass, which is going to be 2 plus 1 plus 4. Okay, so then let's just carry this down a little bit. Watch my math because, hey, it's early for me too. 2 times 0 is 0. 1 times 3 is 1. 4 times 5 is 20. So 20 plus 3 should be 23. Ooh, 23 over total mass. 2 plus 1 is 3 plus 7. It's 23 over 7, right? No, 6. No, 7. 2, 1. Why am I getting this wrong? 2 and 4. We wrote that one wrong. Okay, 23 divided by 7. I'm sorry, I need a calculator. 23 divided by 7 is going to be 3.29. 3.29. Okay, so 3.29 would be just about here, right? That would be my center of mass, because 3 meters gets me to the 1 kilogram block. That 0.29 gets me, just on the edge of that 1 kilogram block. I didn't get a ruler out, so don't say, well, Mr. Well, shouldn't it be just slightly over? Just to confirm, X is your position. Yes. X is all about position. And here we're saying X with that little small cm, that means position of center of mass, the position of the center of mass. And we've calculated it by saying mass times position plus mass times position, all based on left to right. And we do that as long as the problem doesn't tell us otherwise. If the problem tells us to use it in respect to something else, like some arbitrary point, then left of that arbitrary point would be negative and right to that arbitrary point would be positive. What is the unit for the center of mass? It's just meters, because it's a position. It is just meters. Because if you think about it, on the top, you have kilograms times meters, and on the bottom, you had kilograms, right? So the kilograms cancel out, and you're left with meters, right? So this would be meters, because this would be kg times m, and this is kg, right? So the kilograms cancel out, and you're left with meters. All right, if we can accept this, which is not that bad. I mean, it's something new, but it's not awful. That's center of mass. We're going to add in one other thing, and then we're done with notes, okay? And that's going to be the velocity of the center of mass. The velocity, we've talked about the position of it. Now, what about the velocity of the system, right? Because if you think about it, if you guys ever watch like Star Wars or Star Trek, and you got the spaceship, going through space, that center of mass is constantly moving, right? Or let's say it is moving. That center of mass is in motion, so that it has a velocity. But inside the spaceship, you still have people bumping into each other in the hallways. So you still have collisions going on inside the system, but the system as a whole is moving, right? Does that make sense? I mean, even us as people as a whole, we have, if our system is the earth as a whole is moving, even though we don't really, we don't think about how far we actually go when we're going all the way around the sun and back. We're going pretty far away every year. Doesn't feel like it when we're only going home to school, to the grocery store, to the mall, back to home, to school, that sort of thing. So let's look at the velocity center of mass. All right, I'm going to scroll this up just so we can get to that. And let me just title this velocity center of mass. All right, remember cm is center of mass. This is the velocity for the entire system of objects. I'm going to write that one down. Velocity for entire system of objects. All right. If the net force on a system is 0, that means no outside forces, the velocity of the center of mass of a system will not change. Right? Because we need an unbalanced outside force in order to have an acceleration, right? Newton's first law. An object in motion wants to stay in motion. An object at rest wants to stay in rest, unless acted upon by an unbalanced outside force. So if the net force on a system is 0 and there's no outside force, the velocity of the center of mass of a system will not change. The force of collisions are internal, not external, so the velocity of center of mass remains the same. Okay. The people bumping into each other on the Starship Enterprise, if you ever watch Star Trek, does not change the velocity of the Enterprise. Okay. You driving in your car and your brother and sister in the back seat bumping into each other and, like play fighting does not change the fact you're driving 70 miles an hour. Your car would be the system. Everything in the car is the system. That system is moving forward, and the people playing tag on each other's shoulder, those collisions are not impacting the velocity of the system because those are internal to the system. Okay. Now, how do you calculate the velocity of center of mass? So here I'm going to say a V for velocity and then Cm for center of mass. Remember before we did X for position, here we're doing V for velocity. And I like we do the V, right? Yeah, I'm sorry. See, there you go. I'm not the only one that watches Star Trek. It's funny, I can only see 3 people right now, but at least one of them's interacting. That's awesome. How am I going to calculate this? All right, let's look back at the last formula. Let's use it as a guide. Guess what we're going to do? Yes, you got it right. That would be M1 V1 plus M2 V2 plus M3 V3 ... if there's more. In my example above, there was only one. There was only 3. And then I'm going to divide that by what? You got it. M1 plus M2 plus M3. You're just going to take mass times the velocity plus mass times the velocity plus mass times the velocity. And you're going to divide that by total mass. And this will get you the velocity of the center of mass. Now, could we rewrite this a different way? Yes, absolutely. Because what is mass times velocity? Momentum. So we could say that this is P1 plus P2 plus P3 on for every object of the system. And then we would divide that by the total mass. So I'm just going to put an MT here. That means total mass. It's the same thing as adding up each individual mass, total mass. So we can put here, I'll just type this out or write this out, mass total. Okay. Now, I think the velocity of the center of mass is easier once we kind of see the position of center mass, see how it's calculated, and just say, okay, well, going from position to velocity just means we're just going to change the x's to v's. Same thing. We look at each individual component of the system, we divide it by the total mass of the system, and that will get us what we're looking for. Here, the units, since its velocity is still meters per second. I'm gonna give you just a second in case there's any questions you want to throw out there. Make sure you're all caught up. We're going to switch over. We're going to do the first couple of problems in each of the homework assignments. I actually have to alter the second one. So don't jump off and say, hey, I got this from here, because I do need to fix something that would otherwise be questionable. But if we're good with that, I want to get you started on these problems because I want to make sure you're comfortable. The problems are really based on impulse, and it's something that we had already started working on, where the notes centered around center of mass. I want to make sure that we're still good on the calculations for impulse. If we're okay, looks like we're okay so far. Let's take a look at what our homework is. I believe it's this tab right here. All right, let's do the first couple on this one. All right, and let me move my notes to that. Perfect. Okay, unless otherwise indicated, use positive and negative to indicate direction. directions. Okay, so we'll say like right is is positive and left is negative, or up is positive and down is negative, just for simplicity. Okay. For a constant force, suppose the duration of impact on an object is doubled. Okay, so for a constant force, the duration of the impact is doubled. So then that duration, that's going to be time. So this saying basically time times 2. Okay, how does this affect the impulse? Well, we know that impulse is equal to force times time. And if force is the same, but time is doubled, well, that means the impulse is now doubled. And I indicated that with 2J, because J is impulse. And if I double the time, I've doubled the impulse, if force is constant. If force is held constant and time is doubled, well, it's force times time times 2. So the impulse is doubled. How does this change how does this affect the change in momentum? Well, impulse is change in momentum. Impulse is change in momentum. If you're asked to calculate the impulse, or if you're asked to calculate the change in momentum, the question is the same thing. If I ask you, who is your mother's daughter, or who is your father's daughter, it's still you, assuming I'm talking to a girl. Or a boy, I'm saying the son, but it's still you. Same question, same answer. So that means this is also 2 times larger. It's the same question. If you're ever asked change in momentum, or if you're ever asked impulse, impulse is change in momentum. It's one of those things that they try to trick you. Don't be fooled. Okay. All right, let's do number 2 and 3. And I think at that point, you're going to be kind of in the right mindset for these problems. Number 1 was just a warm up. All right, we have a 5-kilogram football thrown by Vince Young. I don't know if you guys remember him. He used to play for Texas. He was really good. I think they won the national title with him. Pretty sure. He didn't do a lot in the NFL, but at one time, that name would have been pretty big. He, with a velocity of 15 meters per second, is caught by a stationary receiver and brought to rest in 0.2 seconds. Okay, so what I'm seeing is I see a mass equals 0.5 kilograms. See, I'm not abandoning the guess method. I still want to list out my given so that I can see and process what's going on. My initial velocity of him throwing the ball was 15 meters per second. It says the ball was brought to rest, so the final velocity is 0 meters per second. It says what impulse is delivered to the ball. So A, what impulse? I know that impulse is equal to force times time, and it's also equal to mass times V minus V naught. Okay, well, I don't have force and time, but I do have a mass and I have a change in velocity. So we can plug that in. That would be 0.5 times, what was it, final minus initial? So final is 0 minus initial of 15. Okay, I think from this point you could solve that problem. So let's take a look at B. How much force must be exerted to stop the ball? Ooh, okay, maybe I do want to solve that with you. Let's get that number. I got negative 7.5 when I did that one, 7.5. Remember, Newton seconds is my unit. So A, I get negative 7.5 is the impulse or change in momentum, whatever you want to call it. Now it's asking me how much force. Okay, so there was a time. Let's put the time in our list. 0.02 seconds. Okay, so my given included a time. Let's go to B. It says how much force must be exerted in order to stop the ball. Well, in A, I stated that force times time is equal to mass times the change of velocity, right? And we solved for the right side of that equation and said that negative 7.5, and they told us that the time was 0.02. So force times 0.02 is equal to negative 7.5 because we solved that in A. In A, we got negative 7.5. So if I take that, if I divide it, I should get that force is equal to, now watch me because I might have gotten this wrong, 375 newtons. I'm going to scroll this up to where you can still see it, but where we can get to number 3. Let me check that. So there's nothing in the chat. Okay, we look clear in the chat. All right, a 1,500 kilogram Maserati. All right, let's get this. Mass equals 1,500 kilograms. Is moving with a speed of 15 meters per second. All right, so the velocity, initial velocity is 15 meters per second. Collides with a utility pole, ooh, and is brought to a rest. So final velocity equals 0 meters per second in a time of 0.3 seconds. Find the force exerted on the Maserati during the collision. Find the force exerted on the Maserati during the collision. Well, we know that impulse is force times time, and that's equal to mass times a change in velocity, final minus initial. Okay, we have everything we need, I believe. 1, 2, 3, 4. Yeah, we do. Okay, so we can say force is equal to mass times the change in velocity over time. Right, I just divided the time over, and I'm solving for force. And we know that change in velocity over time is acceleration, and mass times acceleration is force, Newton's second law. So I'm going to bring this kind of up here, say that force is equal to mass 1,500 times the change in velocity, which would be 0 minus 15, which would be negative 15, divided by the time, 0.3 seconds. So my force then should be equal to negative 75,000 newtons, which is what they got. Now, the next question says, what effect would extending the time of impact have on the force exerted on the Maserati? Okay, now I don't want you to go back to the first problem and say, hey, we had a bigger time, so we had a larger impulse. It was true for that problem because they said force was constant. Let's look at this problem. What effect would extending the time of impact have on the force exerted on the Maserati? Does anybody have any thoughts on that one?
Since the bottom number would be increased, wouldn't the force be smaller?
So the bottom is, yes, it would. Because time is at the bottom of our fraction there, since we're dividing by time, if we increase the time, the force goes down. He's absolutely right. And I'll show you in a different way. You can see it clearly because the way I've written it in A, but let's just go back to impulse is equal to force times time, right? The impulse, the change in momentum for this Maserati is set, right? It is a 1,500 kilogram automobile that started at 15 meters per second and went to 0 meters per second. So the mass times the change in velocity is a set value. The impulse is set. So now if I can increase time, what does force have to do? It has to go down. This is why they have airbags. This is why airbags were designed in cars. It wasn't so that your head would hit a pillow, because believe me, that pillow is going to hurt. It flies out at you very fast. It's not a pleasant experience. But what happens is if you were to be involved in an accident, if there was no airbag, your body would go forward and be stopped very quickly by a seatbelt and your face very quickly by a steering wheel. Okay, so the time would be very short. But what if that airbag comes out and now it takes you longer to come to a stop because it slows you down? It slows you down, meaning it takes more time. When you increase the time, the force is reduced. We do this example in on level with eggs. If I drop an egg on the floor, if I just drop an egg on the floor, it's gonna break, right? But when I drop it in my hand and I kind of cradle it and catch it slowly, it doesn't break, does it? Because I take longer to slow it down to a stop. It still comes to a stop. The impulse is still the same. Its velocity still goes from 10 meters per second to 0. But if I can make that time take a lot longer, the force is less. I'll give you one more example. When you're driving and you see a dog run out in front of you, you slam on the brakes and everybody falls to a hard stop, right? A lot of force. You felt the force of that stop. But if you're driving along and you know there's a stop sign up ahead and you just get off the gas and you coast and then you slowly put on the brake, you slowly come to a nice easy stop. No one is falling forward. No one even really feels the slowdown, right? More time, less force. Okay, that gets us through 1, 2, and 3. Let's go to the other one. I want you to finish this for homework. There's a total of 11 problems. We've done the first 3 together. It's not bad. Let's take a look at this other one. I want to get you started with it. This one's really kind of quick. It just involves some thinking. Okay, I know thinking at school, kind of weird, but it's physics. So every once in a while you have to do something, right? Okay, so there are a multitude of graphs here. 2, 3, 4, there's 6 graphs. And we're basically just going to say, what information can we get from these graphs? All right, now the one that I need to make sure I scribble out is this one right here should have been blackened out. That one should be blackened out. So for your force versus position graph, the units of the slope and the meaning of the slope should be blacked out. That's not, sorry about that. Oh, no, it's cool. I'm glad you came back. So all is well. What we're going to do on this one, let's just pick a couple. I'll do the very first one, and then maybe let's do the first one and the last one together. And then I want you to kind of fill it in because I want you still to go through the thought process. Okay, so on the first one, we have position versus time. So the meaning of the data points, the meaning is just a position at a given time, right? For every data point is telling me a position at a given time, right? So position versus time. The units of the slope, well, that would be meters per second. And the meaning of the slope, if we remember that, come on, it's from the first week of the year, velocity. The slope of a position versus time graph is velocity. Now, remember when that was the hard thing that we were doing in class? Right, this is like, okay, now I want to go back to that person because they had it way easy. Okay, so it's starting with that. The next graph is velocity versus time, then accelerations versus time. Then we have force versus position, force versus mass, and then force versus time. Okay, like I said, I want to do the first one with you, and then I'll do the last one with you. So for the last one, again, it's force at a given point in time is the points. Force at given time. Ooh, let's get an E in there. There we go. Force at a given time, that's the points. Now, the next column that allows me to do it is units of the area under the curve. So the area under the curve would be multiplying force times time. Well, if I multiply force times time, the unit would be Newton seconds, Newtons times seconds. And if we remember, what are we using Newtons times seconds for?
Impulse.
Exactly right, impulse. So this shows us when we get these graphs in a test, if we get a force times time, we know the area under the curve is impulse. We know we can gain that information from that test, right? Well, what I want you to do is fill in the rest of this. Okay, this one doesn't take that long. I want you to just fill in this with the exception of what I scribbled out. There's no right answer there. I mean, units you could figure out, but there's no purpose of that slope. So finish the first one we did through number 11 and work on this one, fill this in. Do that between now and next class.